Imagine for a moment that you are trying to understand how a human brain works, but you are not allowed to look inside. You can only see the inputs and the outputs. That has been the reality of artificial intelligence for years. We call it the black box problem. But someone at OpenAI just did the equivalent of pulling a computer processor out of a block of concrete and finding a perfectly readable, hand-drawn wiring diagram inside. In a stunning new research paper, OpenAI has revealed a method called Circuit-Sparsity. To get there, they did something that sounds completely counterintuitive. They took a GPT-2-style transformer model, trained on Python code, and brutally deleted more than 99.9% of its internal connections. They didn't just trim the fat, they stripped the model down to its absolute bare bones. What survived this digital purge wasn't a broken mess. Instead, the fog of probabilities cleared away. What remained were tiny, traceable circuits that you can actually follow with the human eye. For the first time, we aren't just guessing which neurons fired. We can watch an AI make a decision, step by step, logic gate by logic gate. Let's dig into how they actually achieved this. Modern language model design usually treats reasoning like a massive statistical blur. Millions of weights fire at once. Even if the answer is right, nobody, not even the engineers, can point to the specific memory slot that made it happen. Interpretability researchers usually poke at this fog, hoping to find patterns. But OpenAI flipped the script. They enforced a rule called weight sparsity during the training itself. After every single optimization step, they zeroed out all but the strongest connections. It is a survival of the fittest for neurons. On top of that, they added activation sparsity, meaning only about 1 in 4 internal signals is allowed to fire at any given moment. It is brutal efficiency. Think of it like editing a rambling, messy essay into a tight, devastating poem. All the hedging clauses, the ums and ahs, they all vanish. Only the lines that actually move the idea forward are allowed to remain. In the most aggressive models, only 1 in 1,000 weights stays non-zero. And yet, the model's performance on benchmarks stays comparable to the dense, heavy versions. So, what does this look like in practice? Let's look at the quote-closing task. In a standard dense model, the ability to close a quote mark is smeared across thousands of parameters. It is a mess. But in OpenAI's sparse model, this behavior collapsed into a tiny circuit. Specifically, a circuit with just 12 internal units and 9 surviving connections. You can literally trace the logic. One unit lights up when it sees a quote. Another unit tracks whether it is a single or double quote. A third unit acts as a memory cell, writing that information to the residual stream. It is a machine for a single thought: detect, classify, copy, output. It looks less like statistics and more like traditional computer code. This leads us to a massive revelation about memory. In another test, the model had to decide whether a variable was a set or a string in Python code. To do this, it has to remember how the variable was defined lines ago. In the sparse model, OpenAI found a dedicated subcircuit that literally writes a marker onto the data stream. It is a concrete store and retrieve mechanism. When the code later asks, "What is this variable?" a reader unit queries that specific marker. If they delete the writer unit, the model forgets the variable type. If they delete the reader, the model can't use the information. This proves the AI isn't just hallucinating patterns, it is deliberately remembering facts. Now, you might be asking, this is great for small puzzles, but what about the massive models like GPT-4? This is where the bridge comes in. OpenAI isn't just making small, toy models. They are building bridge networks that translate between these highly interpretable sparse circuits and the massive, dense models used in production. This suggests a future where we don't just train AI to be smarter, we train it to be readable. We are moving from a world of alchemy, mixing potions and hoping for gold, to a world of chemistry, where we understand the atomic structure of intelligence. The implications for AI safety are enormous. If we can identify the specific circuit responsible for a behavior, we can fix it. Imagine finding the specific circuit that causes a model to lie or to be biased and simply disconnecting it. We are talking about debugging intelligence itself using a schematic that we can finally read. OpenAI's Circuit-Sparsity research is more than just an efficiency hack. It is the moment we stopped looking at the outside of the box and finally turned on the lights inside. The future of AI isn't just about being powerful, it's about being understandable. What do you think? Is being able to read an AI's mind the key to safe artificial general intelligence, or will the complexity always outrun our ability to map it? Let me know in the comments below.